Okay, so in order to understand the significance of that possibility of rotation around those single bonds and the broad range of possible structures that that opens up, we're going to move away from DNA for a moment and have a look at this, which is, in a sense, a much simpler system. So this is just a bunch of molecules trapped in a box, moving around, bumping into each other. And this is a reasonable simulation of what happens with molecules in a gas. So you can see that the molecules are coloured, and they're colour-coded according to how much kinetic energy they've got. So if you have a look at one of the white ones, you'll see that it's moving very fast, so that's a high-energy molecule. And if you look at the blue ones, you'll see they're moving much more slowly, so they're the ones at the low-energy end of the spectrum. And the important thing is, if you pick on a white one and just watch what happens to it, you'll see that sooner or later it collides, and when it collides, it tends to lose energy and become converted into a lower energy molecule. Meanwhile, other molecules, as a result of collisions, are getting speeded up. And so, although the total amount of energy in the box is constant, because the box is insulated from the outside world, so no energy gets in or out, but individual molecules are constantly transferring energy to one another. And they're also, of course, constantly changing direction. And so what we see then is this randomization effect, that although the total energy is kept the same, its distribution to individual molecules changes as they collide with one another. What's really interesting is if you look at the graph at the bottom left, which shows you how many molecules there are in each energy sort of range, as the simulation progresses. And what you can see is that although individual molecules are constantly changing from low energy to high energy to middle energy and so on, the total number of molecules in each energy range stays roughly constant. So the shape of that curve, although it's fluctuating a bit, you can see that it stays roughly constant. And the line that's plotted there underneath the fluctuating bars is a time average over the length of the simulation. And that should look very familiar to you, because that is the Boltzmann distribution. So what this simulation actually quite accurately reproduces is the distribution of molecular energies. And it shows you that the Boltzmann distribution just results from this random transfer of energy between molecules. The reason that it fluctuates a bit is because we've only got a relatively small number of molecules in this set. Of course, in a real molecular system, there would be an enormous number of molecules. And as if you've studied statistics, you'll know, the more individual trials you have in a system, the better the statistics are. So if you flip a coin 10 times, you wouldn't be that shocked if you got, say, 8 heads and 2 tails. But if you flipped it 1,000 times, you would be shocked if you got 800 heads and 200 tails, because you would expect the statistics to get closer to 1-to-1 the more trials you do. And it's the same with this. Because we've only got a limited number of molecules in the box, the statistics are never perfect for the Boltzmann distribution. But once you get up to sort of mole-size quantities, then the statistics become much better. So what we're going to do now is just to develop that idea a little bit more by starting this time with a bunch of molecules which have no energy at all, so they're completely static. They're randomly distributed in space here, but none of them has any energy. And we're just going to introduce a single fast-moving molecule and watch what happens. Okay, so in a second, we'll just introduce one molecule, and it'll be a white one, representing the fact that it has lots of kinetic energy, and we'll just watch what happens as it enters this box of molecules that have no energy at all. So here we go. There it comes. And you can see very quickly that that single molecule collided with another one, transferred some energy to it. They then both moved on and collided with further ones, and very quickly the effect of those collisions spreads and spreads throughout the box. And so we start to see a whole range of energies and a whole range of molecules moving in different directions and at different speeds. And pretty soon you can see that it almost looks like the simulation we had before, because the energy has almost become randomized throughout the entire box by now. And that's reflected, of course, in the Boltzmann distribution, which again you can see at the bottom left. So that really emphasizes how important it is that you understand that it's very difficult to keep a fixed structure. So we had a fixed structure to start with, all the molecules weren't moving, but as soon as we introduced just one moving molecule, its energy rapidly got spread out to all the other molecules, and so they all started moving, and so the distribution of molecules is now completely different from what it was to start with. Okay, so finally, one more thing we can illustrate with this simulation. So what we've now done is we've constrained the molecules to occupy just half of the box. So we've in effect pushed a piston down to halve the size of the box. And we're going to watch what happens when we move the piston back up again. And the question obviously is, are the molecules going to tend to stay in the bottom half of the box or what? So let's just do that. So we've removed the piston, and you can see immediately, and you would have guessed this would happen, that the molecules don't stay in the bottom half of the box, that they are rapidly moving up and filling the whole space. And again, what's going to happen is that pretty soon they'll be randomly spread throughout the whole box just as they were before. So again, what this emphasizes is the difficulty of keeping a bunch of atoms in a fixed arrangement, because this random distribution of energy tends to make the atoms spread out. So let's return now to the world of polymers, like DNA, and see what the implications of this idea of random redistribution of energy are for a system like this. So here we've got a model polymer where we just have lots of freely rotating units like those single bonds that we saw in the backbone of the DNA structure. And we'll just watch what happens as a result of the random transfer of energy along the chain. Now this is actually quite a simple simulation, because this treats the chain in isolation. So it's actually making it harder for it to redistribute energy, because it's not being bombarded by other molecules from the outside. It's simply redistributing energy along the chain. But if we watch what happens, you can see that it doesn't hold a fixed structure at all. That as a result of this randomization of energy, the structure of the polymer changes with time. And this emphasizes that it really is very challenging for a structure like the double helix of DNA to exist, because you would expect this sort of random coil to develop. And so what we really need to do now is to pinpoint how it's possible, given that we know it's got these rotatable single bonds in the backbone, how is it possible for it to be pinned down more or less in a fixed double helical structure? So the key to all this, and something we haven't thought about so far, is that not all these different shapes into which the polymer can fold have the same energy. Not least because in some of them, atoms will be getting in each other's way, and those clashes will raise the energy of the molecule in that system, and we'll see what effect that has in a bit. So it's easiest to understand that if we start by looking at a really simple system. So we're going to look at butane, which is this. And basically we're just going to look at what happens if you rotate around this bond here in the middle of the molecule. Because you can see at the end it's pretty homogeneous. You've just got CH3 and CH3, but the interesting question is what happens as you change the angle of rotation around there. So here around the outside in this diagram you can see 4 different structures that you get by rotating around that bond. And you can see in the graph the calculated energies that those structures have, and you can see that they vary quite a lot. So this one has the lowest energy. In other words, this is the most favourable state, which looks like this. So here, this is actually the structure that's shown here. And the reason it's low in energy is that it minimises the extent to which atoms get in each other's way. So first of all, when we look at the hydrogens on the 2 adjacent carbons here, you can see that they're not directly lined up with one another. So where this one coming towards you is pointing upwards, this one is pointing downwards. So they keep out of each other's way. If we compare that with, say, this next structure, we can see there 2 hydrogen atoms which are lined up with one another. And so they'll be a bit closer in space, and that's going to raise the energy a little bit. And that's why you see this energy gap here. This one, again, they're staggered. They're not direct. None of the bonds on one hydrogen are directly lined up with the ones on the next carbon. But nevertheless, it doesn't have as low an energy of this one as this one, because these 2 methyl groups on the end, this one and this one, are now tending to get in each other's way a bit, and that raises the energy. And this is the worst case, because now we've got groups on adjacent carbons lined up directly with each other, so that increases the extent to which they're getting repulsive interactions between them. But what's made it much worse is that we've got the 2 methyl groups directly aligned, and because they're much bigger than just hydrogens, that gives you a much stronger repulsive interaction, and that's why this has absolutely the highest energy. So you can see that as the chain undergoes these energy transfers and moves from one arrangement to another, it's not necessarily moving to arrangements of equal energy. However, these energies here are actually quite small. And what that means is that even at room temperature, a molecule's not going to get trapped in its lowest energy state. That's its most likely state. That's where it will be most of the time. But it can get over this barrier and get into this state or this state, and it can even transiently reach these high energy states here. So the molecule is still fairly flexible, but it will have a preference for being most of the time in this lowest energy state. Now if we change now to looking at pentane, so we're adding one more CH2 into the chain, we now have a more complicated situation because we've got these 2 bonds in the middle of the molecule, again assuming that the ones to CH3 at the end are fixed in this staggered conformation like we saw before. But now you've got 2 bonds in the middle of the molecule about which you can rotate. And so now if we want to draw a graph to show the energy as a function of these 2 different variable angles, we have to draw a 3-dimensional graph like this. So this is a calculated, what we call now an energy surface for pentane, where basically you've got the angle of rotation around one of these bonds listed as θ1 going in this direction, and then you've got the angle of rotation around the other one, θ2, going in the other dimension here, and then energy is going upwards. And you can see now you get this rather complicated potential energy surface with peaks corresponding to the high energy states, and that would be the one where all of the atoms on adjacent carbons are aligned with each other, so there's strong repulsive interaction there. And then you get the dips, which are the lowest energy states, and those will correspond to the most favourable arrangements. And you can see already with just 2 bonds, you've got really quite a complicated landscape of hills and declivities, I think is the word we're looking for there. Hills and dips there, where the dips correspond to the most favourable arrangements and the hills are the least favourable ones. But again, with pentane, the height of these hills is relatively modest, and so the molecule is quite flexible. It's able to get from one dip to another over the gaps in between. It would probably struggle to get over this one, but it can get over the sort of lowest energy routes from one to another relatively easily. So pentane is still quite a flexible system. So far, the only kind of forces that we've thought about which affect the energies of these different arrangements of atoms in a polymer are repulsive interactions where atoms are getting in each other's way. But of course, you can also get attractive forces, and you've in the past thought about these as intermolecular forces, but they can also occur within a molecule if it folds into certain shapes. So here is an example. This is a small piece of a protein, in fact, and what's being calculated here is the effect of rotating around this bond and this bond. So these 2 bonds here. The rest of them have been fixed into what's been assumed is their most favourable orientation. So it's just examining the effect of rotating around here and here. And again, you can see that you get quite a complicated energy landscape, but in particular, you now get some really quite deep dips in the structure. And this one here corresponds to this shape, and you can probably see why this has the lowest energy shape, why this is the lowest energy shape, because this is a nitrogen and a hydrogen, so we have NH, and this is a carbon and an oxygen, so C double bond O. So this oxygen is strongly delta negative, the NH will be delta positive, and we can basically make a hydrogen bond across there. And it's that attractive interaction, that hydrogen bond across there, which makes this the lowest energy state. So once we introduce the possibility of attractive interactions lowering the energy as well as repulsive interactions raising the energy, then we really get the scope for quite complicated energy landscapes.